Okay, so now I think you have all got about the understand pretty much understanding about the material part. Now let's talk about how we can simulate those kind of things. Okay, using those materials, how what kind of technology we have currently with us, right? So just like I mentioned earlier when I was discussing what is optical simulation, uh, so it's all about like interaction of light at different scales. Okay, uh, the size could be could vary from micron domain to a millimeter scale. Okay, and or it could go even more. So when the light actually interacts with the micron level structure, uh, then we call it as a photonic simulations, and we basically we simulate a photonic devices. It could be anything. It could be waveguide. It could be any kind of. It could be a photonic sensors. I mean image sensors. Okay. And also we can simulate the photonic circuits, which is basically comes under the system level simulations. Okay, we can definitely we can design diffractive optical elements. We can design nonlinear substrate where we can study the second harmonic generations or 4F mixings, etc. Okay, so all these things we do in the photonics in submicron levels basically comes under the photonic simulations, and ANSYS numerical is gold standard tool for that. Okay, to do this type of simulation. So basically, this numerical, a small bit history of the numerical. Numerical is a founded by itself a company called Numerical long back ago. But it got acquired by ANSYS in 2020. So from hence onwards, now it become ANSYS Numerical. Now, if I step to the right, so you can see that we have another tool called ANSYS Emacs. I was talking about the optical simulations, a classical optical simulation, where we mostly deal with this lens mirrors, which has the dimension is quite big compared to the wavelength of light. That in that case we use uh, the Zmax. As you can see, the ratio of the dimension by lambda, it's quite high. If you move from left to right, it increases, correct? uh, if we even go farther to the right, we have another tool called ANSYS POS. So basically it's called a system level modeling. So in the system level modeling, what we do is we actually deal with the system, the environmental lighting conditions. We basically, this tool actually helps you to design lighting, the the lighting simulation. uh, okay, how where to place the light and how it looks like in different environmental condition, for example the foggy condition or the night condition or the daytime conditions, and how a human eye can perceive those things. Okay, so these feel actually you will get okay in ANSYS POS. Okay, so it's basically a real-time system modeling. Okay, it's very accurate to our real world, and that is the USP of this ANSYS POS, because when we do the simulations, you also should whenever you're doing this system level modeling, you need to understand, okay, what kind of products at the end eventually will generate. Okay, the prototype basically. So if you make sure before physically designing it, so it gives you a lot of advantage. Okay, so that's the thing, that's what actually Spios does. Okay, so now coming to the numerical, access numerical, I'll spend some time just to briefly explain about the numerical part, what it is, and okay, what are the capabilities, what are the solvers available under numerical. So basically, it's basically a comprehensive set of tools and features for photonics. It allows designers to model photonic components that include interacting optical and electrical thermal effect. Okay, as you can see that in this particular slide, uh, that this numerical consists of different solvers. Each and every solvers has some definite workflow, and these kind of solver is used for different definite applications. Okay, what are these applications? So as you can see that v- numerical starts with first a very a, I would say the very powerful tool, which stands for which known as FDTD, finite difference time domain method. Okay, it provides a gold standard tool for modeling nanophotonic devices, processes, and the materials. FDTD comes with three different solvers. FDTD itself, one is called a stack solvers, and one is called a RCW solver. So RCW stands for rigorous coupled analysis. Okay, this is a bit old slide, so that's why we cannot see this RCW solver. But yeah, right now we have these three solvers together. So, and which makes it more powerful. So you can see, as you can see that this FDTD actually useful. That is most popular and mostly used by the people, by the users, because it has a lot of potentials to simulate, starting from sensors to metamaterials. Okay, as you can see. Uh, so if I come to the, so in FDTD actually we can simulate periodic structure as well as aperiodic structures. Any kind of arbitrary structure we can simulate in FDTD. That's why it is so popular. It has a lot of flexibility. Now, another solver called a numerical mode, which offers to simulate everything you need to simulate the waveguide. uh, FDTD has some distinct disadvantage, uh, not disadvantage, I will say some limitations for simulating very long structure. But just like I already mentioned that this particular tool, this photonic simulation tool, is meant for simulating a kind of micron structure or nanometer structure. But if you have a structure more than the micron level structure, say a millimeter kind of structure, which is very big compared to the wavelength of light, in the some cases actually what happens is the tool it takes time to simulate those kind of big structure. So in that case, to get rid of this kind of problem to some extent, we have this option called a mode, which actually useful for simulating the waveguide, because typically the waveguide is useful for transferring information from one point to another. It could be the length of the typical length of this waveguide could be in terms of millimeter to several kilometers, right? If you're talking about optical fiber, so of course the length is very very high. So what will happen, okay, if I have this kind of very lengthy waveguide, okay, and we want to understand about the waveguide property, okay, how the model profile looks like, how the losses we actually calculate in this particular waveguide, okay, so all sort of things we actually simulate in numerical mode. Okay. uh, so just to give you the brief who doesn't know about this particular tool, uh, that's why I'm just explaining, but it has some definite applications. Just like I mentioned, maybe tomorrow I'll cover that part as well. Okay, how mode could be helpful for for designing waveguide. And one more thing is that when we do the simulations, we need very I told you that uh, first of all, when we simulate any structures, we need machines to do that. We need to assign a lot of memory consuming things. Source, monitors, mesh itself consumes a lot of memory. If the structure is big, then of course it will take more memory to simulate it. And for that case we need a very high performance system, okay, to simulate very effectively your structure. So that's why we need what I would say that a technology which is known as a high performance computing technology, which actually comes with this FDTD, and it seamlessly work with FDTD solver, because FDTD mostly need this high performance computing, because I told you the structure, it could be very much complicated, it could be lengthy, but sometimes actually the length could not be, sometimes the length is not, it might not be the issue. The issue could be the, maybe the complicacy, the complicacy of the structure. If structure is too complicated, for example metamaterials, in that case some changes needs to be done in terms of meshing or in terms of boundary conditions. Okay, so that can make your simulation more longer and more computationally effective. So in that case we need this kind of high performance computing to simulate it very effectively. Then another if these numerical ability and the mode are mostly useful for simulating for simulating in the optical domain. But as you know that I talk about, I said that numerical is basically a multiphysics tool. Why this is called a multiphysics tool? Because it has a multiphysics capability and workflow along with the optical simulations. What are these? These are the basically to simulate component in the charge domain, in heat domain, and in the multi-quantum quantum structure also can be simulated. Okay. So maybe in the next slide I'll explain it more detail. And also we have this interconnect solver. This is basically useful for designing photonic integrated circuits. Ultimately most of the people are working in the right now to design the effective photonic integrated circuits to couple the light effectively inside your waveguide. Okay. How to do that? There are a lot of challenges people are right now facing. They try to overcome it, and that's why we need a robust solution, okay, to understand about the circuit behavior of I mean the photonic circuit behavior. Okay, how it behaves on when how it behaves when all the components integrated together.